All right, this video is all about isotopes and atomic mass, and we're going to point out how atomic mass is different than mass number. So make sure that you see the video on mass number if you need a little more clarification with that. All right, so what's an isotope? An isotope is an atom that has the same number of protons but has a different number of neutrons. So this is kind of updating Dalton's atomic theory. He thought that all of the atoms were exactly the same, and that's not true. They can be slightly different. And the way that they're slightly different is by having different number of neutrons, something that is going to change their mass and not their actual identity. Okay, so he was like, kind of right. All right, so carbon 12, carbon 13, and carbon 14 are the big go-to examples for isotopes. All right, carbon is number 6 on the periodic table, so it has 6 protons. So that means carbon 12 is going to have 6 neutrons, carbon 13 is going to have 7, and carbon 14 is going to have 8 neutrons. Okay, it has one extra neutron for each one of them. So if we take a look at carbon isotopes, you would end up seeing that there is a distinct difference in their masses. And if you take the mass of 12, 13, and 14, and we average them together, what would their average mass be? You would end up getting 39 divided by 3 and a mass of 13 AMU. Well, if you look at our good best friend, our periodic table, what does it say the atomic mass of carbon is? It says it's 12.011 AMU. That's not the same thing as carbon 13. So what's up with that? Well, the thing that it is the atomic mass is a weighted average, okay? Whoops, sorry about that. The weighted average of all of the atoms that are naturally occurring based on their abundance. And abundance means how common they are. Okay, so we have carbon 12, carbon 13, carbon 14. They are all not equally, excuse me, common. So carbon 12 is the most common one. 98.89% of all the carbon in all of the universe and all of the galaxies and our planet and others is going to be carbon 12 with our 6 protons and with our 6 neutrons. Carbon 13 is really rare. Carbon 13 with its 6 protons and its 7 neutrons is only 1.1% abundant. And carbon 14 is like almost negligible, so much so that it doesn't even get into the hundredths column. Okay, it's really only used for radioactivity and figuring out exactly how old things are with like dinosaurs and fossils and all that kind of stuff. We'll talk about half-lives and carbon dating when we get to the atomic nuclear chemistry chapter. Okay, it's really, really rare. So how can I take the average of all three of these when these two are like really not common? So that's where we get this weighted average. And if your grades are determined with a weighted average, that's exactly how it's done. So what we do with our weighted average is we take the relative abundance, which is the decimal form of our percent abundance, and multiply it by the mass number of that isotope. Then we add it to isotope number 2, doing the same thing, and isotope 3 and 4, however many isotopes exist. There are like some atoms that have like, I don't know, 6, 7, 8 stable isotopes. Okay, like sulfur is really big. I think chromium has like 8 or 9. All right, and then you are taking the weighted average, taking into account exactly how abundant it is. Another thing that you'll see is that we're going to formally define atomic mass unit, or AMU. Okay, a AMU is a made-up unit by these nuclear chemists who were really sick and tired of working with 10 to the negative 31st grams and 10 to the negative 29th grams and all these really ridiculously small numbers. And they're like, hey, why don't we define the atomic mass unit based as 1/12 the mass of a carbon-12 atom? Well, if you remember, carbon-12 is 6 protons and it's 6 neutrons also. So it has a mass number of 12. So 1/12 of it is roughly the mass of a proton. It's just going to make things easier. So instead of using grams, it's going to be accurate to say AMU. And it's not AMU, it's AMU. Okay, so what we're going to do is we're going to do a sample problem. Go get a calculator. You want to definitely practice putting all of these things into your calculator, and then push play when you get back. So push pause till you have that calculator. Hey, you're back. All right, so chlorine has two isotopes. Chlorine 35, which is 75.77% abundant, and chlorine 37, which is 24.33% abundant. So what's the atomic mass of chlorine? So chlorine 35 is going to be 75.77% abundant, and chlorine 37 is 24.33% abundant. So let's change these percents into decimals, so relative abundance. So I'm going to divide by 2, move the decimal place over twice, 0.7577, and I'm going to multiply it by my 35 AMU. My 24% abundant is going to be 0.2433, and I'm going to multiply it by 37 AMU. So with your calculators, you type everything in, you get 26.5195 AMU for the first isotope, and we get 9.0021 AMU for the second isotope. And here is your pro tip. Add them together. Okay, when you add them together, you get 35.5216 AMU. Don't average these. This is already averaged. It's already weighted for that. And then you can check your answer on the periodic table. Okay, so hey, bestie periodic table, where are you? Let's take a look at chlorine and see what its mass is. Oh, it's 35.45 AMU. Well, I don't know about you, but 35.5 is pretty darn close to 35.45. The reason why it is not exact is because these have these percent abundances and relative abundance have a lot more decimal places. So do the mass numbers. They actually have a lot more decimal places. So there is some slight rounding error with that, but you get the general idea of how to solve for these. All right, so if we take a look, here is our example typed out so nicely for you. The atomic mass, 35 times your 0.7577, giving you your 26.5, and your 37 times your 0.24, giving you 9, and it adds up to the 35.45, which is, or 35.5, which is pretty close to the 35.45 AMU. And one of the things that I want to show you is this next PhET simulator right here about isotopes and atomic mass. It really helps visualize what we have going on. So if we take a look at the isotopes and atomic mass and click on the sim, if we look at chlorine, if I have one chlorine 35 and one chlorine 37, it shows me a 50 to 50% abundance, an equal average. And the mass would be 35.96, which is not 35.45. So how do I slide this way? By having more 35 chlorine 35s in the mix. If it's a 2-to-1 ratio, 66 to 33, it's 35.6. If it's a 3-to-1 ratio, you'll end up seeing it's almost the same as what we had in our example, and 35.46 is pretty darn close. In nature, it's going to look way more like this. That 35.76 is pretty close to that 24.24, what we saw, that 35.45 AMU. And you can see the wide variety of your chlorines and your 35s and chlorines 37s. Okay, the other example we talked about was carbon. You can see carbon 12, carbon 13 are really, really outnumbered with the carbon 12s. It's so much more percent abundant than your carbon 13s. This example doesn't even have carbon 14 on here. If you go to my mix, you have 12 carbon 12 and carbon 13 in 50 to 50, and you would see that average out to be 12 and a half. Even if you did a 3-to-1 ratio, it's almost not going to get you there. 4-to-1, 5-to-1. If we start dumping all of these in here, it's going to get you pretty close to that 20.01, but not quite there. One that's really interesting is oxygen, okay, because oxygen has 3 different isotopes, oxygen 16, 17, and 18. And we can see that we have our 16, 17, and 18. If they were all equally averaged out, it would be a mass of about 17, 16.997. But it's not. Carbon 16 is far more abundant. So you'll see that the mass of our oxygen, our atomic mass, is going to be 15.999, which is 16. If we go to nature's mix, you'll see how many more purples there are than the red oxygen 18s, and then one oxygen 17 in there. So a really good little simulation getting you back and forth throughout everything. All right, one last thing to show you in our notes is a very specific naming for the 3 isotopes of hydrogen, and it's important that you get these straight. All right, there's a hydrogen 1, a hydrogen 2, and there's a hydrogen 3. They're all hydrogen, so they all have 1 proton, but they differ in their number of neutrons, like we saw. Okay, hydrogen 1 has 0 neutrons, hydrogen 2 has 1 neutron, and hydrogen 3 has 2 neutrons. Okay, hydrogen 1 is the most common one, 99.985% of all of the nitrogen and all of the universe and all of the galaxies and all of the world is hydrogen. Okay, it's normally called hydrogen. Some people like to be fancy and call it protium. But it's really only just going to be 1 proton and 1 electron. Okay, but remember, the electrons are so much smaller that it doesn't account for any of the mass. Okay, hydrogen 2 is heavy hydrogen. It's only 0.015% abundant. There's not a lot of it, and it's called deuterium. So you end up getting your mass of 2. And really heavy hydrogen is tritium. It's almost impossible to find. If you are a fan of Marvel in Spider-Verse, Doc Ock is going to get a whole bunch of tritium, and he's going to try to harness and make their own energy source with the sun, and everything kind of goes kablooey. I won't spoil the movie for you, but that's the general premise of the idea of our tritium. Okay, so heavy hydrogen is used a lot to mark specific hydrogens in different kinds of chemical reactions. So they can isolate and make sure that this one is going to be deuterium, and then you can see where it enters another molecule if you're doing some other kind of reaction with it. So it's really useful in our lab setting, but it is something that you should know the difference of. Okay, the most common mistake is that they think that deuterium is going to have 2 neutrons. It doesn't. It has 1. You have to account for the mass of the protons. And they think that tritium has 3 neutrons when it doesn't. That has 2. All right, so that is isotopes and atomic mass.